Okay, hi folks. Um, let's talk logarithmic functions, I guess. So in grade 11, you guys kind of did exponents and exponential functions, and then we just sort of told you you could use the log to solve for an unknown exponent, but we didn't really explain what on earth you were doing or what you were working with. Um, so I guess I'll run through the quick review at the top. Hopefully you guys remembered these ones. So your product rule, you can write it out in words if you'd like. I'm not going to try because it'll be a mess. Is basically that rule where if you have the same base raised to different powers, you can add the powers. Okay, so that's your power rule. I'm just going to make my marker less thick. Your quotient rule, same idea, but you're dividing and you're subtracting. So you can subtract the exponents as long as you have like bases. So just remember those two rules require the same base. The power of a power rule is the one where you have like a base raised to an exponent raised to another exponent, and you can just multiply your exponents, okay? And then negative exponents mean that they take the base and flip it. So they take the reciprocal of the base. And sometimes you guys remember that as it's 1 over. That's true if your base is like a whole number, but if it's a fraction, it just flips the fraction, and then the exponent becomes positive. Rational exponents are a different way to write roots, so we did talk about that a little bit earlier on, right? We've been down this road. And then you did tons of these in grade 11. So if you have a fraction in your exponent, b over c, it would be like the root of the base raised to the power of the numerator. Okay, so the denominator is just the index in your root. And then anything raised to the power of 0 equals 1, no matter what it is. So hopefully you remember those from last year. You spent a decent amount of time playing with exponent rules in grade 11 and like solving those nasty looking expressions with exponents everywhere. We're not doing that this year. We're talking about it more from a functions perspective and then like a real life applications. So the beginning of this chapter is pretty disjointed because we're kind of hopping all over the place. But the key takeaway is to understand that there's a logarithmic function, and all that it is the inverse of an exponential function. So it's not the reciprocal, it's the inverse where you reflect it over the line y equals x, or switch your x and y coordinates to get there. Okay, so really this y equals log of x, and this is the base, so it has a base of 2, so log base 2 of x, could also be written as x equals 2 to the y. So it's literally just the red function, take the inverse, so switch your x's and y's, and it'll produce your logarithmic function with the same base. Okay, so looking at the one that's here, if you're talking about your domain, you're going to tell me that x is all real numbers such that x is greater than 0. It's not ever going to be equal to 0 because we know that our exponential function never touches the y-axis, right? Because 2 to the power of something won't equal 0. The same is true for your log, so your x value is never going to be 0. Because when you rearrange this into exponential form, it's 2 to the y equals x, so there's no way that 2 raised to a different power is going to produce a 0. So that's what's happening there. And then your range would be all real numbers. Okay, so y, e, r. Your asymptote this time is the vertical, so it's at x equals 0. So your exponential function has a horizontal asymptote at the x-axis. Your logarithmic function has a vertical asymptote at the y-axis. Okay, because it's literally just the inverse of this. The x-intercept is 1 because the y-intercept of the exponential function is 1. Okay, and this one obviously doesn't have a y-intercept. Intervals of increase and decrease, it's always increasing. Okay, so that doesn't change when you take the inverse. So it's increasing when x is an element of 0 to infinity. And make sure we don't include 0 at all there because, again, that's an asymptote. Okay, so they relate to the properties of the exponential function in that they're basically the opposite. Your exponential function has a domain of all real numbers and a range that's greater than 0. its asymptote is at y equals 0, it has a y-intercept at 1, and it's also always increasing. So they're connected the same way we would expect for any kind of an inverse relationship. Okay, now this is where it gets like kind of, you just have to trust me for a couple days until this all starts to make sense. So I just showed you the inverse in exponential form. You just switch x and y. So we know that you can do that. And the base of a logarithmic function can be whatever it wants, just like the base of an exponential function can be whatever. So you just have that a there for that reason. To rewrite your inverse in logarithmic form, basically what happens is that the base remains the base, for lack of a better way to describe that. So here, my base was a. This little piece here is called the base as well. Okay, so this is the base of your logarithm, or like the value that you're using when you're thinking about your logarithmic scale. So the spot where you guys have seen logs before probably by now is chemistry. When you're doing pH, you're taking logs and you're working on a scale that is base 10. So a lot of times you deal with a base 10 scale for this, but it could be anything. So that's what that A is. And then I kind of remember it as when I'm trying to write it in logarithmic form, I want to have y by itself on one side, right? And then I can do that by taking the log of both sides. So last year you learned to take the log of both sides. Once we talk about the change of base formula, the reason for this move makes more sense. For now, just kind of remember that the base remains the base and then x and y sort of swap sides of the equal sign. And then I'll show you where that comes from later on in the unit, okay? The exponential form is actually easier to work with from like a problem solving perspective. So if you look over here, basically when you have something like this, it's almost easier to think of it this way. So don't get too hung up on the x's and the y's. Just know that here you'd be thinking like, you know, a to the power of what would equal x. So like here, 5 to the power of x equals 125, and then you know that that's 3. So that would also be the solution for something like, if we wrote this, it would be your log with a base of 5 of 125 equals x, right? So these are equivalent statements, and I know that x would have to equal 3 here. So therefore, I know that this thing would equal to 3. Okay, so that's kind of when I'm solving logarithms, I'm not usually thinking in logarithmic form. I'm usually thinking about it in its exponential form. My next note there is just inverse of an exponential function is a logarithmic function. Similar to when we were working with reciprocals or inverses of parabolas or whatever, I'm going to tell you that if you can work with the exponential function, that's way more familiar, do that, and then just take the inverse later, okay? If you guys have to write the equation of the inverse in exponential form, you just switch x and y, and then to write in logarithmic form, use the formula above. Again, I will show you where that comes from as we go, I promise. And then I have an example with numbers. So you have an exponential function as y equals 6 to the power of x, so your base is 6. In exponential form, it's x equals 6 to the power of y. And then in logarithmic form, your log just has to have a base of 6. Okay, so you're just taking the log of x with a base of 6, and that's going to equal to whatever this exponential value is, and that's kind of why I showed you that example there. Again, this gets clearer as we go. Every time we start a new function, it seems kind of like weird, but eventually it all makes sense, okay? So the practice problems here are basically just trying to get you to understand what this graph looks like. The math will come later. But if you're going to sketch the graph of y equals 1/2 to the power of x, remember that that's the same as like 2 to the negative x. So y equals 1/2 to the x is similar to, or is identical to that. Okay, so it's just 2 to the x reflected over the y-axis, right? So we know our intercept is at 1. And then I know that 1/2 to the power of 1 is 1/2, and 2 is a quarter. And if I put it to the -1, I would have 2, and -2 would give me 4, and so on and so forth. And pretend like I can draw on this tablet here, okay? There. Okay, so that's the exponential function. And then the inverse is going to be your logarithmic function. Okay, so it's telling me to write the equation of the inverse function in exponential and in logarithmic form. Okay, so we started here y equals 1/2 to the power of x. So now I'm going to go 1/2 to the power of y, okay? And then when you go to write it in logarithmic form, again, just follow the pattern. So you're going to put your y over here. The base of my logarithm is 1/2, and that's okay. And then the x goes there. Okay, so that's it written in logarithmic form. And then to graph it, remember, if you're sketching the graph of an inverse, you're just flipping your coordinates of your points, right? So here we were at 0 and 1. Now we're going to be at 1 and 0. Okay. And then at -1, we were at 2. So that means that at 2, we're going to be at -1. Okay. And then at -2 was 4. So at 4, we're at -2. Right. And then at 1 was 1/2. Right. So at 1/2, we're at 1. So it's similar to the graph we just saw. It just feels funny because it's pointing this way, but we still have that same asymptote that we talked about, the y-axis, and there is your graph. So this is your logarithmic function. Okay, but it's also just the inverse of the graph that we already knew how to draw. Okay, so that was kind of just an introduction for you guys to sort of see what graphs of logarithmic functions look like. It is a bit of a pain in the butt to graph them, especially depending on the base. So when you are sketching those graphs, when your base is something like 10, they get very steep very fast, and those numbers get very small very fast. Okay, so just be warned about that. But again, the point at the start of the chapter is just to introduce you to the concept of a logarithmic function.